Good evening, colleagues, and welcome to the latest in Inaugural lecture series. Tonight, Professor Chris Sansom will be talking about Save the World and Discover New World, which fits very nicely with his job now here at Derby as our theme lead for Zero Carbon. So what I'd like to do now is introduce you to Professor Mark Jolly from the University of Cranfield, who will introduce Chris for me.
Thank you very much, Paul. Good evening, ladies and gentlemen. It's really wonderful to have been invited here to introduce Chris, with whom I worked in Cranfield for very close to 10 years. Chris was brought up in Wales, but makes no claim to be Welsh, as he was born in Solihull in Warwickshire, and his parents were English, but they moved to Rhyl when he was 2 years old. Chris's father was an aircraft engineer at what is now Airbus, and his mother ran the boarding house where they lived. So at school, Chris loved sports as much as science, and he even played hockey for Wales, despite being English, and at county level tennis. In science, in particular, he liked anything to do with heat and light, and says he's been working on that ever since his A-levels. As an indicator of things to come, he bought a 4-inch reflecting telescope and joined the British Astronomical Society, using the money he'd earned during the school holidays on stacking deck chairs on Rhyl Beach and working as a waiter. Chris eventually obtained his degree in physics from Liverpool University and his PhD from the University of Sussex, carrying out research on the topic of infrared detector materials. His PhD was funded as a collaborative award in science and engineering. We call those CASE awards nowadays, or even iCases, I think. And it was with Plessey Research Labs, who offered him a job in their infrared detector research group after his PhD, and who also turned me down for a job after my PhD. So Chris moved to the GEC Research Labs, and after 2 years, and stayed with GEC Marconi for 20 years. His research at that time was mainly in manufacturing, focusing on the fabrication of gallium arsenide semiconductor devices for the telecommunications applications. And most of this work was obviously carried out in clean rooms. For Chris, these were very interesting times. A number of government ministers toured the facility, and on one notable occasion, the Prime Minister of Malaysia came, and Chris notably gave him a tour of the clean rooms, accompanied by 2 guards with automatic weapons, and Chris had to wipe those down with lint-free cloths before allowing them into the clean rooms. To this day, he does not know whether they were loaded. When Marconi collapsed in 2004, he spent some time in a number of different positions, as an operations manager, a quality manager, as an engineering manager for both Amazon, of all places, and PerkinElmer. And at Amazon, he was the operations manager on the night shift at Marston Gate, which is very near Cranfield University, which was the only Amazon site in the UK at the time. All the parcels coming off the night shift between 2004 and 2006 were his responsibility. So any outstanding complaints from that time should be sent to him at the end of the lecture. With 4 parcels per second coming off the lines at Christmas time and 400 staff to manage, Chris says he learned to make very quick decisions. Eventually, in 2007, an offer came to join academia as a senior lecturer at Cranfield University, and whilst there, he began in what was called the Precision Engineering Institute as the Knowledge Transfer Manager, and was the MSc course director. He developed his research portfolio around waste heat from machine tools and into energy harvesting generally, and then eventually into solar energy. After a fortunate meeting with academics in Egypt whilst on holiday there, he discovered concentrating solar power, CSP, which has been his research focus ever since. In January, Chris told me he was about to retire because I was essentially working very closely with him and he'd been part of my setup and we were still very close. And we co-supervised some engineering doctorate students. And he was going to cut back his hours. But then he was headhunted by the University of Derby and he told me it was too good an offer to refuse, Paul. So he says he's left to be the head of the new theme in net zero carbon that is one very close to my heart and my research, as I have some very big research portfolios from the UKRI in this area. The latter role overlooks the university as a whole in terms of net zero and gives him the opportunity to build something completely from scratch. So Chris's retirement will have to go on hold for a while. He's married to Sarah, who used to be my information specialist at Cranfield, and a wonderful woman. And they live together in Norfolk when he's not in Derby or North Wales or somewhere else with some strong direct sunlight. But now it gives me great pleasure to invite Chris to share his thoughts on how to save the world and to discover new ones. Chris.
Gosh, how to live up to that introduction? It's going to be hard, isn't it? Thank you very much, Mark. Yes, I had a great time at Cranfield University, and I'm looking forward now to my new career. Well, started my new career here at University of Derby, and very happy to be here. When I look at the title, it sounds very pompous, doesn't it? Please don't think that I'm going to save the world on my own, because I'm not. That won't work. But it just occurred to me when I was thinking about what to talk about and how to frame my career, if you like, so far. And that was that you used to hear people say things like, "Well, we can either save the world or we can do that." But now I think we should think about saving the world and finding another world. So it's the "and" that's important in that title, because there are opportunities now both to improve the world that we all live in, for obvious reasons because of climate change, greenhouse gases, and so on. But also, as you will see from the latest ground and space-based telescopes, there are opportunities to look for new worlds in the future. And it's by sheer chance that my career has touched both of those things. And it was by chance. I'm very envious of people who say that they planned their careers, because I certainly haven't been able to do that. My career has been all over the place, and you've got a good idea from Mark some of those things. I mean, 2 years at Amazon is not something you would plan into your career perhaps as a scientist. But at the time, they were recruiting scientists because they felt that some of their processes demanded a scientific approach. So that's why they recruited. Anyway, I'll get on with the talk, and perhaps you will understand, I hope, how the saving the world and saving this world and finding new worlds has been part of my career so far. So I did start in research labs. I started at the Plessey Research Labs, which you can see on the left, at Caswell near Towcester. Plessey moved their research from central, well, it was actually in Ilford in 1940. Ilford in 1940 had some problems with planes flying over, dropping bombs on it, so they thought that was not a very good idea. So they moved their sensitive radar materials research to Caswell, which nestled in a little valley just outside Towcester. And so I started at the Plessey Research Labs working on infrared detectors. And it looks very pretty in that picture on the left. That's what it looked like in the winter. I took that in the winter in around about, must have been, I guess, around mid-70s, I suppose, that sort of time. And that was one of the days when we couldn't get into work because it was snowed in, so snow everywhere. So having nothing, there's not much to do in Towcester on a snowy day, so we decided to walk to work anyway. It took us about 4 hours to walk there and 4 hours to walk back, and that was a day's work done as far as we were concerned. It's still there, it's a business park today, and so you can still go there, and there's still some interesting research that's done there. As I say, I worked in the infrared, and if you look at the timeline for infrared detectors, I worked around this time. I was actually a bit later than 1970. I'm not quite as old as this might indicate. I worked more around that time on lead telluride, and lead tin telluride, which my PhD was on. So I just continued with working on my PhD work in the research labs on infrared detectors, and they looked something like that there, as you can see. That was a single element infrared detector. Peaked at, I think, detectivity around 10.6 microns, which is a human being. A human being radiates to about 10.6 microns of wavelength. So they were looking for people. So this is basically, unfortunately, military application, looking for people hiding in battlefields. I'm pleased to say that my military work did not last too long, and I was able to move on to more peaceful applications. I then moved on to GEC Research Labs, as Mark has mentioned. This was in North Wembley. Sadly, this is no longer there at all. This is, I understand, I haven't had the heart to go back and look. I think this is blocks of flats now, but it was one of the main research labs in the UK back in the, right up to the 1980s. For the early 90s anyway, it was still there. That's a picture taken in the 60s, and that one when I was there in the 1980s. And they did industrial research, a bit like university research, but without the teaching, if you like. In that one, I was working, as Mark said, in clean rooms. I was working in clean rooms at Caswell too, semiconductor industry. So that's basically how I started working in the semiconductor industry, wearing these bunny suits, as we used to call them, working in yellow light. Most of the day you come out into the daylight and think, gosh, what's that? Been working in artificial light all day long. It was a lot of fun, and we were definitely considered to be very much state-of-the-art in what we were doing. We were working on something called MMICs, monolithic microwave integrated circuits. You'll have those in your phone now. You'll have those gallium arsenide and indium phosphide devices in your mobile phones today. They were quite new at the time. I said I worked on heat and light, and even then I managed to find some way to work on heat and light, because I worked on what we called wafer steppers, which transferred the patterns from the masks onto the wafers using deep ultraviolet light. So even that was light in 60 to 70 form. And I've always managed to find, no matter where anybody has put me, not always by choice, I would always find a way somehow to get involved in heat and light, because I think they're easy to understand. After my little sojourn into Amazon and various other places, when Marconi, unfortunately, GEC collapsed, the company of GEC, which was a real shame for the country, I have to say, because GEC had so many 100,000 engineers or something incredible worked at GEC, and we were all basically out of work one day. And a number of us, I suppose, working in research labs, the obvious place was to end up in academia, because we did research. And I was lucky enough to be offered a job at Cranfield University, as Mark mentioned. I had all these wonderful titles, as you could see, like senior lecturer, knowledge transfer manager, course director. I was supposed to do all of those things. I'm not sure I did all of those. I tended to concentrate more on the senior lecturer bit, and I suppose the short courses is what I tended to do most of. Short courses because I liked working with industry, I liked working with companies, which is very much part of the job I'm doing here, of course, so that was good training for that. I liked working with companies doing knowledge transfer, and I liked teaching students as well, and developing master's courses in this case. Because at Cranfield there are no undergraduates, only postgraduates, so it had to be masters and PhDs. So I was part of this new development called the Integrated Knowledge Centre, the IKC, government funded, EPSERC funded, in ultra precision and structured surfaces. Sounds very, very grand. But it's really advanced mechanical engineering. And I went for the interview, and they said, you know, were you interested in the job? And I said, well, I'm not an engineer, I'm a physicist by training. I don't know anything about machine tools, and I don't know anything about ultra precision surfaces. They said, oh, don't worry, you'll pick all that up. I thought I consider myself rather fortunate to get the job. And it soon became clear that I needed to do something rather more than teach my students. This is the first cohort, actually. That's me on the right, looking a little younger, not that much younger, a little younger. That's my first cohort. We had no students on the course at all when I joined. We joined in, I think it was April I joined, and the course was due to start in October. And there was no course, and there were no students. So my job was to develop the course and get it through all the approvals very quickly and find some students. These students I found at recruitment fairs generally looking for work, and I persuaded them that they really wanted to be the world expert in ultra-precision structured surfaces. And I think that's, so if I'm good at anything, it's probably selling and marketing, because they all came on the course. I'm pleased to say I keep in touch with most of them, and they're gainfully employed, so I don't think I misled them. Ultra-precision surfaces, what do we mean by that? I just thought I'd divert into this for a second, because it's quite interesting in the finding new worlds. Precision surfaces are used for, or interesting, for a whole new generation of products in a number of different areas, such as big, large mirrors. That's actually a lens from a wafer stepper from the semiconductor industry. That's obviously wind turbine. That's an artificial joint. Surface of that is very important to the wearer, the person actually using the artificial joint. And you've got large area displays. I'll come back to that one. And obviously aeronautical engineering applications. The surface can make a big difference to the performance of some of these types of products. And that was what the IKC was all about. These are some of the machines tools that were used. And this is one which actually I'll come back to again because it's called a large CMM, a large coordinate measuring machine. It's a large measuring machine. But this one's actually at the time, it was the most accurate large CMM in the world. This up here is called a grinding machine, the box grinding machine. It's called a box because it looks a bit like a box. It's also called a box because it stands for big optics. Very clever. It's big optics. This, when it was built, was the world's most accurate large grinding machine. And the two of these together made ground mirrors for very large ground-based telescopes. That's what it was for. Which is really exciting. Biggest telescopes in the world were made. The mirrors were ground on this piece of equipment. This nano centre, these machines were built at Cranfield, by the way. That one wasn't. You can see it's got lights on it. But these two were actually built at Cranfield. The nano centre was used again for parts for the James Webb Space Telescope, which I'll come back to. So, and by ultra precision, we meant 1 part in 10 to the 8, which is scary. That is amazing. If you think about metre scale, that's hundreds of angstroms. That is incredible. That these machine tools could machine metals, glass, whatever, too. So that was that. I wouldn't claim to be a precision engineer. I've already told you that I'm not. But I was definitely part of the activity and proud to be part of that activity doing such interesting work. And this is part of the Find New Worlds, if you like, because the James Webb Space Telescope, which of course, as you know, was, you'll remember, it was launched on Christmas Day last year. So the James Webb is looking for Earth-like planets around nearby stars. That's what it's actually doing, amongst other things, of course. It's an infrared telescope. And Cranfield produced this thing, or a number of these actually. These are called image slicers for the MIRI. The MIRI is the mid-infrared instrument in the James Webb Space Telescope. It's an image slicer, and then there's a recombiner in here as well, which we also made, but I didn't show you. So that is one of the things that I guess touched my career in terms of trying to find ways in which we can find other worlds, if you like, other planetary systems around nearby stars that might support life and might support human life. I mean, this is a NASA space telescope. It's a NASA telescope. And believe me, NASA do not come out of the US for parts if they don't have to. So it shows you the expertise that there was and probably still is at Cranfield today in precision machining that was able to make that part. And they were delivered on time, and they're now, some of them are in space, even as we speak. 159, yeah, very good. So I was really proud to be part of that. And also, at that same time, we were working on these large mirror segments for what will be the largest telescope in the world when it's built. It's not at the moment finished. And this is the European Extremely Large Telescope, the EELT. Astronomers have a very odd sense of humour. You have to remember they don't get out at night because they're sort of up there in their sheds looking at the stars, so they have a weird sense of humour. We had the LT, which was the large telescope. Then we had the VLT, which is the very large telescope. And now we have the ELT, which is the extremely large telescope. And the one that was never built, unfortunately, I'm really sorry it was never built, was the OWL, the OWL. The OWL is good. Owls can see it in the dark, of course. But can you guess what the OWL stood for? The overwhelmingly large telescope. Yeah, it was designed, but the owl was never built, and what a shame. Yeah, that was. But it's a nice story, isn't it? The overwhelmingly large telescope. Anyway, we'll have to make do with the extremely large telescope for the time being. It's an order of magnitude better than any other telescope, or it will be when it's built. And Cranfield's job was to grind and, I'm saying polish, but it wasn't, to grind and flatten out after grinding. I'll say polish, but we actually had a different technique. Grinding and polishing of large mirror segments for the EELT. That big box machine I showed you was the grinding machine for that. And then it was polished either by chemomechanical polishing or by a plasma technique, which we developed for the polishing side. And the large CMM actually measured it, because if you're going to make precision parts, you have to be able to measure them. So this again was the other part of Find New Worlds, if you like, because the EELT is looking for exoplanets, as they call them, Earth-like planets. We'll be looking for Earth-like planets around around nearby stars as well. That's obviously being built at the moment, and the primary mirror. It's got 5 mirrors in there, believe it or not, bouncing light backwards and forwards. The main mirror is a 39.3 meter mirror, but it's not a single mirror. It's got 980, I think, facets, 1.4 meters across, hexagonal in shape, to make up that primary mirror that looks like it's one mirror, but it's not. It's segments with each other. And it has a number of 4 other mirrors as well that bounce the light until it reaches the focus. Very exciting, and in the Atacama, of course, as you would expect, usually things are in top of mountains, in deserts and so on. And yeah, I guess that's quite interesting. Bearing in mind I spend a lot of time in deserts now, that's going in the desert as well. So that's the part relating to Find New Worlds, really. I had to do some research, though, while I was there, and I decided to work on energy harvesting, which is what Mark alluded to earlier. So I was looking at how we might harvest some energy from these machine tools. So that's how I started out in energy, really. That went soon led me to look at energy more generally, I suppose, and energy wastage, how we can use less energy efficiencies and so on. And it was then I had this famous holiday in Egypt, which everybody knows about these days, where I went on holiday to Egypt and invited myself into the Helwan University in southern Cairo. It's not the university you would normally go to. It's certainly not for tourism. It's in the most dusty, grimy part of Cairo you can imagine. But I was happy to go there, and I gave them a lecture on precision engineering, and they looked a bit aghast. And at the end they said, well, thanks a lot, but I don't think we're really into precision engineering for large telescope mirrors in the dusty parts of southern Cairo. But we are working on concentrating solar power. Are you interested in that? I said, I have no idea what that is. So they told me, and they said, we're writing a proposal at the moment for a big EU project. And I said, that sounds interesting. So they started to talk to me about that. And believe it or not, that holiday was how I started working in concentrating solar power. So I say, some things are planned, some things happen by accident, and that happened certainly by accident. They put us up at Helwan University, by the way, overnight, and I don't think this guest room had been used for about 10 or 15 years, a long time, and everything was covered in dust. Everything in the room was covered in a thick layer of dust. And they very kindly put some fruit and drinks out for us as well. So everything is covered in dust. You could have an orange in the dust, you can have an apple in the dust, you could have water in the dust, but you had to have dust because it was everywhere. We didn't eat any of the things. So what they were talking about was this. This is concentrating solar power. So this is where you take direct sunlight and you use very large mirrors to direct the sunlight onto some kind of focal, either a focal line, in this case with a parabolic trough, or up there onto that, or if you have heliostats around a tower, as they're called, these mirrors direct sunlight to the top. And it's a power station, basically, just like any thermal power station after that. Once you heat up something in your absorber, you then have the basing that you can create steam, generate steam through a steam generator, through a turbine, generate electricity. So they're power plants, but they use sunlight instead of burning coal or fossil fuels and so on. And that's what I got involved with, believe it or not. You won't find any of those in the UK because the strong direct sunlight is not good enough. So it has to be a hot and sunny country. So I tend to go over to hot, sunny countries a lot, and you'd be surprised how many people wish to accompany me on those trips when I do. These parabolic reflectors that we spend so much time working on, of course, are not new. In fact, concentrating solar power is about 100 years old as well. But because of climate change, and because of the need to reduce greenhouse gas emissions and so on, they've suddenly found their time in history. We go right back to Archimedes, who, it is said, burned the Roman fleet using parabolic mirrors, not lenses, but mirrors. So you can see how far back. We all understand the power of the sun, I think, from magnifying glasses and so on when we're younger. But Sarah and I were in Hunstanton a couple of weeks ago, and we found this claim that Hunstanton claims to have the world's first parabolic reflector. So I think that's rather a bold claim, but nevertheless. And the interesting thing is, of course, it's the only part missing from the lighthouse today. So the light has long gone from the top there, but as you can see. So these things have been around for quite a long time, but their time has finally come. My job in this project that the Egyptian people very kindly let me take part in started out as a thermoelectric device, energy harvesting again, waste heat from one of these very large storage tanks here, where they stored the heat transfer fluid that's heated up in these pipes here that the sunlight focuses on. So it started out, and they said this will be about a £50,000, €50,000 project. You know, you can do that bit of the project. And I thought, this is an opportunity though, because I'm working on large mirrors, remember, and these are all large mirrors. So I thought, I've got the most accurate CMM in the world. I could measure these mirrors more accurately than anybody else. So by the time I'd finished, this is sales again, isn't it? By the time I'd finished selling our capabilities, we were in this project for €750,000. So it suddenly became the first of many EU projects that I then worked on. So we developed a technique to measure these mirrors, mirror facets, because they're in individual facets, to measure these on the CMM, as you can see. As you can see in that right-hand picture. And we also developed a photogrammetry technique using one of my PhD students, that was his work, to measure the shape of the mirrors. So we can measure the shape of the mirrors very accurately in the lab and measure the shape of them actually in situ as well. And this became something that we started to take around the world. And so this is, here we are in Egypt, which is where this demonstration plant was built. You can see it's Egypt because they've got pyramids in the top left on this science park. And for some reason they built one upside down. I have no idea why. And this is what it looked like. That was looking in one direction. If you turned round, it looked like that in the other direction. And that's where we built the plant. And there's me with one of my colleagues from Egypt measuring the reflectance of one of those mirrors. So we set ourselves up to provide this service of measuring the shape, the form of these parabolic mirrors and also the reflectance as well. And we were asked to qualify those mirrors when that plant was built. And if you go to that plant in Bourg el Arab, if you're not far from El Alamein, not far from Alexandria, the plant is open and you can go and look round it and you'll see it's got Cranfield University logo above the top. That's some information. I won't go through this now because we're going to run out of time, but the interesting thing perhaps to note is that the total collector area was just under 10,000 square meters. You need 10,000 square meters of mirrors to generate 1 megawatt electrical, basically, 3 to 4 megawatt thermal. So for 1 megawatt, you need 10,000 square meters of mirrors. That's a lot. And that is the one drawback of this, is you need a lot of land to build these CSP plants. But fortunately, they're usually in deserts where nobody cares. Their land is cheap anyway. But if you try to build one of these in California, which we have, there are some in California, that's tougher, because land's expensive there. But there are, if you look at the areas where we can build them, then they are in the hot, basically what we call the solar belt, which is mainly between the two tropics, or around the two tropics, not necessarily equatorial because it's too wet there. But all around California, Nevada, Arizona and so on. The Bahamas, perfect, South America, South Africa too, all across Spain, southern Mediterranean, the MENA region, North Africa, Middle East, India, some of China, Australia is very good as well. All those countries have CSP plants. You may not have heard of them or seen them, but they're there. Skip that one. That was just looking at some of the applications. But I'm going to show you some pictures of other applications of CSP other than power generation. But I'll leave that for now. So just very quickly, I'll just show you a few plants, a few pictures of these plants. So there are 50 of these CSP plants in Spain alone, 50 of them. Mostly built around the same time, around 2014, 15, 2016. And they're all quite similar and they're all about 50 megawatts in size. So these are some of them. They're not all parabolic troughs. Some of them are tower systems like this, where the heliostats direct sunlight up to the top of the tower, where there's an absorber which then heats up in fluid that then goes away to a steam generator and a turbine generator and so on. These are the Abengoa PS10, PS20s plants. Very early, 10 megawatts, 20 megawatt size of the plant. They were quite early systems. I've been there. I've been up the PS10 tower. Believe me, you don't go up those towers until you have a good look at where the mirrors are pointing, because it gets somewhat hot up there. And when we got up there, everything was melted at the top as well. So yeah, the lift up the tower was a bit of an experience as well, but that's another matter. I think things had got a bit askew in all the heat. So that's the Abengoa plants. That's the Hemisolar plant near Seville. If you fly into Seville Airport anytime, you might well see the light from the Hemisolar plant. It's quite close to Seville. I just think these things look very picturesque, and certainly when they're lit up, they do. They look very, very picturesque. These are now in the MENA region. This is the Shams plant in Abu Dhabi. I'm very fortunate to have seen that one. That's quite an impressive plant as well. The biggest plant in the world, CSP plant in the world, is now in Morocco, at Ouarzazate in Morocco. That's got a huge PV plant there as well. That's in South Africa. I haven't seen that one. I've been in South Africa, but I haven't actually seen that plant. That's in Australia, where I certainly haven't been. I've never been to Australia. It's actually a hybrid with an existing power station, so integrating the two. In India, that's what they call a linear Fresnel type arrangement of flat mirrors pointing upwards to an absorber. That's in India, and a big program in India on solar. That's the Ivanpah plant in California. I'd been there, but we weren't allowed to go inside. We just had to look at it from outside. That's a map. It's in California. That's the plant where there was a lot of bad publicity about this one, about birds being caught in the sunlight and birds being killed, which what they do is they defocus them when they don't need the heat. They defocus the light and focus it somewhere else other than on the tower. And they focus it somewhere in the air. And if birds fly through that, they will be killed. They'll be vaporized. So they've stopped doing that now. They don't do that anymore. But the story persists. So there you go. Sometimes bad publicity is difficult to change people's perception. I talk to people about this plant many times, and they say, "Oh, that's the one that kills all the birds." I go, "No, it used to." That's another view of it. This is quite similar. This is the Tonopah plant near Las Vegas. This one is quite similar in its design. I was fortunate to be there when they were building it, so I was lucky enough to wander around the heliostats. They won't let you do that now, but I was lucky enough to do that. The size of those heliostats, they are enormous. Each little dot on there is an individual heliostat, an individual mirror. You can see the size of these. CSP has, you can say, well, so what? I mean, but PV is better, isn't it? PV is cheaper, which it is. PV is cheaper than this type of stuff. So what's the advantage? Why on earth would we be doing this if PV is so much cheaper? And it's about storage. It's much easier and cheaper to store heat than it is to store electricity. I know you can pump water up hills and you can do very clever things to store electrical power, convert it to something else, but it's so easy to store heat. And when you've taken the heat from the sun and you're heating up a fluid, which you can then store it in these big tanks, which is what they're doing here. And all those CSP plants, or most of those CSP plants I've shown you, operate 24 hours a day, all night as well, because they generate an excess of heat during the day, which they then store in these big tanks, and then at night they extract the heat through heat exchangers from these big heat stores, steam generator, run the turbine, generate electricity at night as well. So these plants operate round the clock. You can't do that with PV. It's certainly not, as it says here, this is storing around about 1 gigawatt hour of energy. 1 gigawatt hour of energy. You try and store 1 gigawatt hour in battery. Good luck. It's not easy, but it's very easy to store it as heat. So that's the big advantage that these things have. One day somebody will invent really cheap, simple and cost-effective electrical storage, large-scale grid-level electrical storage, and then I'll be able to go home. But until then, these have a big advantage. So, and this is just showing the same thing really. PV is very good at filling in. This is a time from midnight to midnight, if you like, and during the day, PV is really good. PV will generate electricity for you. But what do you do during the night? What do you do here? This peak time, it's between 6 and 9 o'clock when everybody goes home and switches everything on. How does PV help you there? And there are plans for some CSP plants not to generate at all during the day. Just store their heat and run at night, and just do it that way because of the heat storage advantage. And as it says here, the cost of storing heat compared to electricity is it's about an order of magnitude times 10 difference. Anyway, to move on, there are now many more plants being built. This was all quite new in the 2008. This is when all the Spanish plants were built. 2008, 9, 10, 11, they came on stream. And as you can see, more and more countries are now building these plants. So it's very much a technology of its time. So what can we do? We're in the UK. How on earth can I contribute to that? How do we contribute to that? Well, as I say, we do measure we can measure the shapes of these mirrors. Here's a result of some photogrammetry where we measure the shape, the errors, if you like, in this mirror, and we found there were some errors, but these are quite small. These are about 0.3 at the most, 0.3 of a millimetre, which doesn't really matter, to be honest. This is not precision engineering. So that mirror was actually okay. That's a mirror that went into the plant in Egypt, by the way. That same mirror, same time. Here we are in Italy, actually doing some photogrammetry on a test line in Italy. Not the sunniest of days, as you can see, but so we can do this anywhere now in the world. We can do these measurements, measure the shape of the mirrors to see if they're reflecting in the rays to the right place on the absorbers. So we measure the shape of them. Here we are in Spain doing a similar thing. I may not be very tall, but you can see how big those mirrors are. About 7 meters high, 7.5 I think meters high. They are huge. Believe me, again, if you stand there, you make sure you know where the sun is before you decide to stand there, because very often we're doing work on these mirrors and you smell burning and you realise your trousers are on fire or something. Has been known. Here we are in Saudi Arabia doing the same thing. This is in Jeddah, on the top of the desalination plant at the KAU University in Jeddah. Being English, I've got my tie on. I have taken my suit off, but jacket, but I'm still wearing my tie. About 45 degrees or something like that. And, we're in the shade there. My friend there from the university came out for the photograph and quickly went back downstairs and said, I'll leave it to you then to measure the mirrors. So he left me up there on my own. This is in Pakistan, other end of the scale really. This is a solar cooker. So it's what we call a linear Fresnel. It reflects sunlight from these mirror strips onto an absorber above, which is then used to heat oil, which goes through a heat exchanger for a solar cooker. The interesting thing about this one is it cost nothing. The glass was found on a rubbish tip. You got the bits of glass off rubbish tip, and the metal was metal that was lying around, and it was just done virtually for no cost whatsoever. It's a very cheap solar cooker. And I asked when we made it and we tested it out, and you can see it wasn't wasn't very well aligned. It hasn't got a very good focus up there, as you can see. When I phoned up my friend about a year later, I said, "How's it performing? How's it working now?" And he said, "Oh, somebody stole it." You think you've got everything sort of under control, and somebody walks off with your solar cooker. So, there you go. So I'm afraid we lost that one. This is also in Saudi Arabia. That's a very odd kind of design of a kind of mini heliostats pointing up at a mini tower. And something, Saharaddin would be interested in this because he works on modular towers, mini towers. This is, we ought to have a word with them at the KSU. This wasn't very well aligned either, as you can see. It's not very well aligned. You can see it doesn't point at it should all point at a point, but it doesn't. So we told them that, and they've redesigned it, and I need to go out there again sometime to retest it and see how it's working now. Okay. I should just say a word for my friends in Spain, because we can't really, when we come to do outdoor work, we have to go outside the UK. And I like to say that my outdoor lab is in southern Spain, which it kind of is, but that's only because my friends in Spain let me go there and use their facilities for nothing. So I would just like to say thank you to my pals in Spain. They work at this, this is a big research centre, big government research centre in southern Spain, where we have test lines, test tower, test lines of troughs, heliostats, all sorts of things. Well, I've got materials out there under test at the moment. And it's near, it's in the Tabernas Desert, if you've ever been to southern Spain. It's near Almeria, which is too far from Malaga, I suppose. In the Tabernas Desert. There's one desert in Europe, and that's it. It's classified as desert. So that's where I tend to go for outdoor experiments. And here we are with my pals from Spain, Germany. We're doing some work there, comparing our different reflectometers to measure the reflectance of mirrors. We've got 3 different instruments, and we're trying them out there. And, you can see we've taken every opportunity to shelter under the mirrors. That was a scorching hot day as well. That was so hot. Oh yes, we also got involved in cleaning of mirrors. These mirrors are all covered in dust all the time. That's one of the disadvantages as well. So we got involved with cleaning these mirrors and how to clean them more efficiently. And they just use, at the moment they use these things, these brushes and water. And of course what you haven't got much of in a desert environment is water, precious resource. So they use brushes and water. So we got working on ways in which we could use less water. Do more efficient brushing and cleaning of the mirrors, and that's what we can simulate that process in the lab using a robot with brushes on the end, and we can try different sorts of brushes, different amounts of water, and we try different sand and dust to see which is the most efficient way of cleaning these mirrors. And sometimes they don't use brushes, they just use jet washers. Well, that's easy to simulate. We've got a jet washer. We can simulate that in the lab too. But we always use the real sand and dust from the environment. So I became a bit of a collector of sand and dust. And if anybody ever goes on holiday anywhere and you find some interesting sand or dust, can you bring me some back? Because I do collect sand and dust. Most people's amusement, because it's different. There's red dust or sand from red sandstone from Arizona there. That's from Almeria. It's volcanic, almost black sand, black dust. And then these are the more usual sands that you probably recognize in the world. And we look at different types of reflectors. All the reflectors I've shown you, all those mirrors are all thick glass. Very heavy, expensive, thick glass mirrors, because otherwise in that heat they would distort. They're back silvered as well. You can't front silver them because that would just get blasted off in the installs. So they're all back silvered, so the light has to go through the mirror and then back hit the silver and back out again. So we looked at other things, other ways. We looked at polymers, composites, all sorts of other reflecting materials as well. And that's quite an ongoing, an interesting ongoing experimental route for us at the moment. A lot of work on that. So we were looking at how we could clean these polymer films without damaging them, without scratching them with the sand and dust. And that's what those published that work. Also got involved with trying to find ways to prevent the barriers, trying to find ways to prevent the mirrors from getting sand and dust on them in the first place. So we came up with these ideas for dust barriers around the plant, aerodynamically shaped barriers that would make the dust and sand behave in certain ways, go up in the air or maybe stop them dead at the barrier. So we came up with all sorts of ways of doing that. Porous barriers were the best, about 50% porosity, with a barrier roughly the same height as the parabolic trough. Seemed to work the best. This was a European project. We did CFD modelling first of all to see which would be the best ideas, and then we went into a wind tunnel which we built ourselves. We built our own wind tunnel. You can see it's made of wood. We built a wind tunnel and we made some barriers out of 3D printing, some model barriers to go into the wind tunnel. So we went from theory to wind tunnels to real world, and we built those then outside in Almeria. you can, the PSA as it's called, Plataforma Solar down rear. And we tested them out there to see which shape performed best. The next step after that is to build the full height ones at a real plant, which is what we're trying to do, negotiate that at the moment. We also compared them with a real barrier, real bush, but ours were better. This was awful. This was bits came off this bush in the wind, so we're better off with the artificial barriers. Anti-soiling coatings as well, something we've looked at. Again, you might think that how do you stop the mirrors from getting dirty? Maybe you could use anti-soiling coatings. So these are copolymer type materials, two polymers, one sticks to the surface, the second bond sticks up, it's got a negative charge on the end. Most dust particles are negatively charged, so it repels the dust. That's the idea. So we worked with this company called Chamelic on those. I found out recently that Chamelic had gone bust, which tells you how effective that was. Unfortunately. It didn't work very well, but it's something I think we ought to be pursuing in the future. And things like anti-soiling coatings and dust barriers do have applicability in the UK. I was at Breeden Hope Cement Works the other day, and there's lots of dust. We were trying to stop dust from getting into the plant, but they might be wanting to stop dust getting out of the community. So there's opportunities there to do that work, even locally here in Derbyshire. I'll probably skip one or two of these, but I'll finish with the solar furnace, because I've been talking about power generation, but there are other things you can do with concentrating solar. This is not really a concentrating solar plant. But it's such an interesting piece of equipment. This is the big solar furnace built in Adeo in south of France, not far from Perpignan. It's about an hour's drive from Perpignan. It's got heliostats that direct sunlight onto this huge parabolic set of parabolic reflector, but it's made of many segments that then reflect that light into a point. By the time you've done all of that, you've got something that's well over 3,000 degrees Celsius. So this is really high temperature research is what it's used for. So I'm using it in an example of a nice parabolic solar reflector, but it's used for high temperature materials research. Temperatures that you normally find when close to the surface done. So it has other uses, but it's such a fun place to visit. If ever you get a chance to go there, it's really interesting. It's got a number of floors, and the time I was there, the lift had broken, so they made us walk all the way to the top. So good exercise, I can tell you. Much better coming down. But that's a solar furnace. You may hear about that at some point. It makes the news sometimes when there's some new discovery. A material that behaves very unusually, perhaps, at very high temperatures. It probably came out of a furnace like that. Solar cookers, a couple more examples. That's the Pakistan solar cooker again. The other two are box cookers. This cooker here was a project that we did at Cranfield, where Miriam, who was a student at the time doing her master's course, got an award for this one, Eureka Award for this. Not for the design of the cooker, to be fair, because you can get that off the internet. But we came up with a way of trying to justify how a sub-Saharan African country could make 1 million of these cookers and deploy them in their countries at almost negligible cost. I mean, it's a frightening fact that over 1 million people die every year in sub-Saharan Africa from inefficient kerosene stoves. And and overhead is blistering sunshine. And whatnot, make use of it. Just to prove the concept, Miriam cooked a chicken dinner at Cranfield. It was a nice day, as you can see, because you see from what she's wearing, it's a sunny, hot day. But she made a chicken dinner and we ate it and we all survived. So the experiment was successful. Some other things you can do with concentrating solar. This is very interesting work that was done with a company. I can't remember their name. UK company, a small startup company, and they were looking at extracting biofuels from microalgae. So algae, microalgae, which you can farm. If you put that algae with water into a tube and you heat it up to around about 320 Celsius, which is what we did in this. This was actually done here in India, at Kota University in Rajasthan. We did the experiment. You actually heat it up, then reactions take place. Now to the other end comes something a bit like palm oil, plus something that you can use as fish food, which is big industry, fish food. Something you can feed to fish, and some other unwanted byproducts like some gases as well. But nevertheless, that really has taken off, and a lot of people are very interested in this. That's something that more of. And this is just an example of a very small desalination unit, water purification desalination, boiling seawater, basically, and then distilling it again, pure H2O. Come back to that. So desalination, this is a British Council project, which we haven't made yet. We designed it and published it in conferences, but we haven't actually built it yet. And it was to come up with a small desalination unit or water purification unit for refugee camps, disaster zones, could be dropped in containers into those areas, basically trying to save someone's life. So it's not designed as a highly durable, long-life product. It's designed, made from plastic lenses to concentrate sunlight onto an absorber, and you then store that heat, and when you need to, you use the heat to go through hot pipes. Seawater is sprayed onto the hot pipes, water evaporates, and then gets blown by a fan into a condenser and condenses out as pure water, H2O. And as I say, we designed that, but we haven't actually built it yet, so we're hoping to do that. Small-scale desalination. On the other side, though, the other end of the coin, is something, the work we've been doing with Solar Water PLC. If you Google Solar Water and look at their website, Solar Water are a massive business now, building a huge desalination plant in Saudi Arabia at NEOM, and also planning to build one in Jordan too. That started out as a student project at Cranfield. Started out as a student project. A few students working on it, building a little model. It's evaporating seawater, again, using solar. And then distilling it, condensing it again. But it's a good example, I think, of how universities, it's what you dream of in a way, that you can start out with a student project that will grow into a multi-million-pound business and make the university famous and all the rest of it. Doesn't happen very often, but you have to work with 100 companies at least to get one that does that. But it's a nice story, I think, of how the university can play that role. And finally, I have finished. This is heat storage. Heat storage, of course, has, I talked about grid level storage. I talked about gigawatt hours of storage in those hot molten salt tanks. But storage generally in the UK can be done. We can store heat in the UK too. I don't know why we're not doing more of this. Obviously all the heat comes in the summer and we want to heat our homes in the winter. So it makes sense to store that heat. And there are a number of ways you can do that. One of the most interesting, if you look on the Grand Designs programme, we worked with a guy in Milton Keynes who built his own house and effectively buried it under the ground. Open to the sun, otherwise it's all, you put earth on top of it, and the earth is separated into using polythene sheeting under the ground, and they are heat stores, and they keep I spoke to him recently, and he, having just got through this last winter, and he had no heating on all winter. His house was kept warm by the earth. He's got pipes everywhere, and he piped lots of heat in the summer into there in the winter, in the summer, so it was ready to pump back in the winter. So I'm not suggesting it was easy or cheap to do, but he reckons it costs less to build than a normal house. So I think I'll challenge him on that at some point. But it did make the Grand Designs programme, so it's obviously, I think heat storage, seasonal heat storage, has a role to play in the UK too. And I am talking to a number of councils around Derbyshire at the moment. on these kinds of things. We have worked on other types of heat storage too. One of the most interesting is magnesium sulfate heptahydrate, which is Epsom salts. You can buy it in a chemist. And probably shouldn't tell you this, I'll get into trouble with health and safety, but if you take up Epsom salts and you bake it in your oven, basically you're driving off those water molecules, and you then keep it in a nice dry, airtight environment. And then a few months later you go back and put those dried Epsom salts in a beaker and pour cold water on. They will absorb the water, the heat will come out, and that water will go up to 60, 70 degrees Celsius. Heat storage, there you are, you've got a seasonal heat storage. Epsom salt heat. Okay, so now that brings us kind of full circle. My CSP work continues with my team, and Zaharuddin's here to represent them today. That work continues, but now my work on renewable energy at Cranfield broadened out from solar into renewable energy. Now I find myself at Derby working on anything to do with renewable energy, but even broader than that now. Now we're looking at how we can help the East Midlands, Derbyshire, B2N2, Derby City, whoever, North East Derbyshire. We're working with all of these people at the moment, trying to help them on their journey to net zero or even zero carbon. And that includes as well at Derby, of course, all the people working on climate change and on carbon sinks and any other way of extracting carbon from the atmosphere as well. I feel very privileged to have worked on not just looking at ways to save the world and find new worlds, but also now an opportunity to perhaps spread some of this knowledge out to more locally. I still enjoy my international trips and I enjoy my international work, but it's nice to kind of come home back to the UK now and have the opportunity to share some of these ideas with people in Derbyshire and in East Midlands. I've been, as I said to you right at the start, I didn't plan any of this. It kind of happened to me. But I'm very glad that it did, and I'm very happy to be here today and take you through some of these ideas. Thank you very much for listening.